So let's start off. We're going to start off with four definitions, and I'm going to draw you a picture to show what they mean. So our first definition is for absolute, and they're sometimes called global, maximum and minimums. So we're going to say let, and this is a definition, let C be a number in the domain, we're going to call the domain D, of some function f. Of some function f. Okay, so then the number f of C is either the absolute or the global, and I typically use the word global, absolute or global maximum if f of C is greater than or equal to f of x for all x in D. And for B, it's called the absolute or global minimum. Maybe absolute or global minimum if f of C is less than or equal to f of x for all x in D. So this is our first definition. Let C be a number in the domain of this function f, and we call the number f of C the absolute maximum if f of C is larger than every other value from that function, larger than or equal to, and it's the absolute minimum if f of C is less than or equal to every other value we get from that function f. Our second definition is for a local max slash min. So once again, the number f of C, and we're talking about the same f of C up here, the number f of C is a local max if f of C is greater than or equal to f of x when x is near C, and a global min, or a local min, I'm sorry, if f of C is less than or equal to f of x when x is near C. Perfect. So we have these absolute maximums where f of C has to be bigger than f of x for all x in the domain. And a local max or min is just when x is near C. So I'll draw a couple pictures to show you what I mean. The first one is we're going to have this function. So this is some function f, and its domain is every value between this number and this value of x. So everything right here, including the endpoints, is our domain. So you are only going to have one absolute maximum and one absolute minimum. You can have multiple that have the same value, but you wouldn't say You wouldn't say -3 is an absolute minimum and then -1 is an absolute minimum. So let me show you with pictures. The absolute minimum is the lowest value we get from our function. And right here, this is the lowest value. It has the lowest y value. This is our absolute min. Move that. And the tallest value, the highest value, is our absolute max. Or global min and global max. Locally, we have a local maximum right here. And we have a local min right here. Because for every value of x near this point, this y value is the largest. And for every value of x near this point, this value of y is the least. So at all of your bumps, wherever you have a turning point, you're going to have a local max or a local min. Some of them might be global, some of them might not be. So for example, if we had the function that looked, say, like this, and that we're closed on these endpoints, now we're going to have a global max, and I'm just going to call it G, well, GM doesn't make sense. We'll call it, actually write it out, global max, right here, because that value of y is the largest out of every y value we get from this function. And down here, we have a global min. Because this value of y is the smallest y value we get from this function. We also have a local max. We have a local max here. We have a local max. And we have another local max. We also, right here, have a local min. So this can also be tricky. Something to be aware of is that functions like this that are continuous for everywhere. I want to talk about this point up here. This is not a global max. This isn't a local max. This isn't any kind of max. Since it's open, and we're going to say that this has an x value of 2 for the sake of argument. Here's our origin, 0, 0. Since it's open and it increases, there's no minimum value of x we can plug into this function f that would give us this maximum value. By that I mean we could plug in, not 9, we can plug in 2.001, we could plug in 2.0001 or 2.000001 or etc. We can have a whole bunch of zeros, and from this graph you can tell that all of these y values are going to get larger and larger and larger. When we have an open interval, we can't get to that maximum point. If you pick some y value, I can pick a value of x that gives us a value of y that's even larger. So, be careful on open intervals. This is not a local max. And it's not a global max. So some more examples. If we had, say, f of x being equal to the cosine of x, this function will look like this. Forever and forever, it's going to oscillate from +1 to -1. So this function has infinitely many local, and it was supposed to go straight over. I'm sorry, that's a poor sketch. So this function is going to have infinitely many local maximum points, and it's going to have infinitely many local minimum points. So we have infinitely many local and global max and mins. So each of these is a local and a global maximum. It's a local max because if we consider an open interval around this value of x, this y value is bigger than all other y values in this open interval. It's also a global max because if we consider every value in the domain of cosine of x, that value of y is larger than or equal to every other value of y. Similarly, but opposite, these are local mins because when we consider small neighborhoods, small open intervals around this value of x, this value of y is less than every other value of y also in that interval. It's also a global minimum because if we consider every real number, this y value, which happens to be -1, is less than or equal to every other y value that this function gives out. So local, you're looking locally. Global, you have to consider the entire domain. So this is technically example 2. Cosine was example 1. Example 2 is f of x is equal to x squared. We get the basic parabola. Goes through 1, 1, and then 2, 2, 3, 4, and 1, 2, 3, 4. But it does that forever. So this function has an absolute minimum or a global minimum. Because remember, these two are the same thing. Absolute or global. So it's an absolute minimum because f of 0 is less than or equal to f of x for all x. Since it's a polynomial, its domain is all real numbers. F of 0 is less than or equal to f of x for all x. So f of x, or f of 0, I'm sorry, is the global min. F of 0 is also a local min. Because if we were to consider this interval, and by this interval, the reason why I'm not giving you specific numbers is it is largely arbitrary. For local maximum and minimums, use a more intuitive approach for finding them. We can say this rigorous definition for global minimums and global maximums if this problem had one. But for local minimums, look at your graph. Look for the bumps. All you have to do is be able to define some open interval around a bump to be able to say this. So we get this largely from observation, or I'm going to encourage you guys to find your local mins by observation. We're going to come up with more techniques later on, but for now you can do it by observation. Just look at the thing. Visually, it's a local min. It looks like a dip point. F of 0 is also a local min because for all x near 0, f of 0 is less than or equal to f of x. So we have this global min because out of every element of the domain it's the smallest number, and we have a local min because when we look near that value of x we get this minimal value. But for maximum values, this function does not have a maximum value. It doesn't have a maximum value because no matter what value of x you pick, there's always another value of x that gets mapped to a larger number. Same thing is true over here. Whatever value of x you pick that maps to what you say is the maximum number, there's always another value that gets mapped to a larger number. So, globally, there isn't going to be a max. For a global, you need a closed interval. Let me say what I mean by that. For global, you need a closed interval for an endpoint to be a max or a min. Over here, the endpoints, well, this continues on to positive infinity and continues on to negative infinity in the opposite direction. Since the domain is all real numbers of polynomials, all real numbers is the open interval from negative infinity to positive infinity. You will only ever have an endpoint being a global maximum or minimum if the domain is closed. Going back to this example, we had an absolute minimum and an absolute maximum at the endpoints on this problem because our domain was closed. Let's revisit this because it lends itself to the point I'm trying to make. I'm going to draw my attempt at the same thing. The only thing that's going to change is instead of dots, we have open circles. So now this value of x is not in the domain, and this value of x is not in the domain. Now our domain of this function f is the open interval from here to here. Like I said, these two are supposed to be the same thing, aside from we lose the endpoints. Our domain is slightly smaller. Now, all we have is we have a local max, and we have a local min. And I'll make those dots. But now in this problem, there is no global minimum and there is no global maximum. No matter what value of x you pick that goes with the largest value of y, there's always some other value of x that gets mapped to a larger value of y. And you can pick a larger value of x that gets mapped, and a larger value, and a larger value, and a larger value. Similarly, but opposite is true over here. You can always pick a smaller value, and a smaller value, and a smaller value that gets mapped to smaller and smaller values of y. So, the point I'm trying to say is, in order for your endpoints to be considered a global maximum or minimum, you have to have a closed interval. This open interval and this open interval, you know you will not have global maximum or minimums at the endpoints. Perfect, I hope. Let's see what is next. So, example 3. Is f of x is equal to x cubed. And we're going to revisit this example once or twice throughout this lecture. Go through 1, 1, goes through 2, 3, 4, 5, 6, 7, 8, and negative 2, 3, 4, 5, 6, 7, 8. So we kind of look like this. And now, right here, and this actually bottoms out more, right here, we have neither a global max, no global max. We don't have a global max because no matter what value of x you pick that relates to the largest value of y, there's always some other value of x in the domain of this function that goes to a larger value of y. So there is no global max. Similarly, there's no global min. There's no global min. You can't get the smallest value out of this function. This thing limits to negative infinity, so there is going to be no global min. There's also no local max. And there's no local minimum. So we have no global max because there isn't a, we have no global max because there isn't a highest value, and there's no local max because if we say this is the largest y value, if this were a local max, then we should be able to construct an open interval around this value of x, where there's no other values of x that go to a larger point. And you go, well yeah, if we pick this point of x in that open interval, clearly it goes to a larger point. I had to bend my line to even make it on the graph. So, no local max. For a local max or min, you need a bump. By a bump, you need something that goes up and then goes down, or down and then goes up. You can have a local max there, and similarly you can have a local min over here. So just to be aware of. So the next we got a couple theorems. The first theorem is the extreme value theorem. And so what the extreme values theorem says is if f is continuous on a closed interval, a to b, and that was a poorly drawn square bracket, then f attains a global max and min over a to b. And so what is meant by this? Let's draw some pictures. We have two cases. So case one is f is constant. If f looks like this, and we'll say that this is a, and this is b, and this is f. So f is the constant function over this interval. Well, in order for there to be a max, a global max, f of c is a global max if f of c is bigger than or equal to f of x for all x in between a and b. And it doesn't matter which value of x we choose. I'll pick this one right here and call it c. F of c is clearly as big as, as big or equal to as every other y value that we get. Every y value is the same, so really f of c is equal to f of x for all values of x. Therefore, f of c is a global max. But we also have, let's say, f of d is a global min if, and I gotta go down, f of d is less than or equal to f of x. And once again, it's this or equal to. And so it doesn't matter which value of x we pick, I'll say that, and I keep on trying to draw b. We'll pick this one, call that d, and here is f of d. Now clearly f of d is less than or equal to every other value of y, so f of d is a global min. This isn't supposed to be a trick. Our global max and our global minimum is the same thing in this example. So the other option is that instead of f of x being constant, f of x is not constant. If f of x is not a constant, then it can look like this. I wanted to do that on purpose. So, here's our domain. Here is our A, and here is our B. So our global max is actually going to be way up here. This is our f of, our f of c. F of c is our global max, because f of c is greater than or equal to, f of c is greater than or equal to every other y value this function gives on the domain a to b. And this value down here is what I've called f of d, because f of d is less than or equal to f of x for every other value of x in this problem. So, if we have a continuous function, you are guaranteed these values. What happens if we don't have a continuous function? Well, the theorem can't tell you any information. For example, this function has a minimum value. It has a global minimum value. It has a global minimum because out of every other value of x, this is the smallest value of y. But there is no global max. There's no global max. Because whatever value of x you pick, there is another value of x that gets you a larger value of y. So no global max, because we're not continuous. Similarly, a function that isn't continuous on a closed domain, such as this function neither has a global max nor a global min. No global max, no global min. So our theorem is talking about functions that are continuous on a closed interval. We're not continuous on a closed interval, so our theorem doesn't tell us anything about this function. And we're continuous, but just not on a closed interval, so once again, our theorem doesn't tell us anything about that function. We've got another theorem by Fermat. Fermat has a lot of theorems. He's was a number theorist. Fermat's theorem, and you'll hear about Fermat's theorem, you'll hear about Fermat's little theorem, you'll hear about Fermat's big theorem. Fermat's, like I said, he's got a lot of theorems. What Fermat's theorem says is that if f has a local maximum or minimum, at C, I assume, at C, and if f prime of C exists, then f prime of C is equal to 0. Perfect. So be careful about looking into Fermat's theorem too much. So the condition is if it has this local maximum or local minimum value at C and f prime of C exists, then you know about the value of the derivative. So this function has a local minimum right here, and if you look, the tangent line is flat at that point. This is our f prime, and this is our f of C, and this is our value of C. So what it's saying is if we have this local max or local min at that point, then the derivative exists, then you know the slope of the derivative is equal to 0. But you have to go through these conditions in order. So for example, and now example 5, I don't think I labeled example 4 for you. Example 5, well, jumping back to f of x is equal to x cubed. And then if you look at the drawing that I painstakingly drew and then immediately lost. F of x is equal to x cubed. Looks like this. And this drawing is better because it shows that this thing really does go more horizontal. If we take the derivative of x cubed, we get 3x squared. And if we set the derivative equal to 0, that would imply that x is equal to 0. So what it's saying is we have a horizontal tangent line at the point 0, 0. But this isn't a local maximum or a local minimum. So be careful. You have to have the theorem says that if you have a local max and min, then you have the derivative equal to 0. And finally, what they call example 6 is the absolute value function. F of x is equal to the absolute value of x. So clearly, this function is not differentiable at 0. We'd have the limit from the left as h goes to 0 has to be equal to the limit as the right as h goes to 0. This function is not differentiable at 0, but f of 0 is both a local and global minimum. So be careful. The thing about Fermat's theorem is that, let's see, what does it say? Fermat's theorem does suggest we should at least start looking for extreme values of f at the numbers where the derivative is equal to 0. So by that I mean, we really use the contrapositive to Fermat's theorem. So let me write that down. So the contrapositive to Fermat's theorem. So what is a contrapositive? So theorems are logical statements of the form if blank, then blank. If something happens, then something happens. What the contrapositive says, and I'm going to call this A, and I'm going to call this B. If negative B, then negative A. So these things are logically equivalent. If it's sunny outside, then I hike on Baldy. If I don't hike on Baldy, then it's not sunny outside. So they're logically the same, but they're said in opposite orders, and they're negatives. Talking to a child, if you eat your vegetables, then you can have dessert. The contrapositive would be, if you didn't get dessert, then you didn't eat your vegetables. So the same thing said opposite and backwards. So Fermat's theorem says if f has a local maximum, so where's x cubed? Where did I write? So Fermat's theorem says that if f has a local maximum or minimum at c, then and f prime of c exists, then f prime of c equals 0. The contrapositive says if f prime of c isn't equal to 0, then f does not have a local minimum or max, or f prime of c does not exist. One of the two options. If the value doesn't equal 0, well, it's possible that that value doesn't exist at all. But for certain you know, if the derivative doesn't equal 0 at that point, then you know there's no local minimum. And that's more of the strength of this theorem. Fermat's theorem is used to go from wondering about all of the points where your local maximums and minimums are, and it boils it down to a few points that you have to check. So, the contrapositive to Fermat's theorem really gives rise to this definition that we're gonna use. This definition is for a critical number. So what a critical number is a critical number of a function f is a number c such that either f prime of c is equal to 0 or, oops, not capital F, or f prime of c does not exist. So by the contrapositive to Fermat's theorem, it says that if this derivative isn't equal to 0, then we don't have a local maximum or min, or the derivative doesn't exist. What a critical number is we care about all the points where this derivative is equal to 0. Those are going to be part of the points we're going to check. We're also going to check wherever the derivative does not exist in our attempt to find these local maximum and local minimums. I don't know if I've explicitly said that, but these critical numbers are used to find local maximums and local minimums. So example 7. Let's find some of these critical numbers. Let's say f of x is equal to x to the 3/5 times 4 minus x. So, if we want to find these critical numbers, we want to figure out where either a, the derivative doesn't exist, or b, where the derivative is equal to 0. So regardless, we're going to have to take the derivative of this function. On one hand, we could use a product rule, but that might get kind of clunky. We can distribute that x to the 3/5 across subtraction, and we would get 4x to the 3/5 minus x to the 3/5 times x is x to the 8/5. Now, when we go to calculate our derivative, f prime of x is equal to, we'll say 4 times 3/5 of x to the negative 2/5 minus, we would say 8/5 of an x to the 3/5. And so this is our derivative. If we want to set this thing all equal to 0 to solve for x, what we get is, I'm going to combine 4 with 3 to get 12/5 of an x to a negative 2/5 minus 8/5 of x to a 3/5 is equal to 0. Perfect. So at this point, I'm just going to multiply both sides by 5 to clear out some of our fractions. Because you're free to manipulate this equation to your heart's content to make your algebra a little bit easier. 12x to the negative 2/5 minus 8x to the 3/5 is equal to 0. So what I also want to do is I can go through and I can multiply both sides of this equation by x to the 2/5. X to the 2/5. So x to the 2/5 times 12x to the negative 2/5 is going to just leave us with a 12 minus 8x to the 3/5 times x to the 2/5 would give us minus 8x to the 5/5, or 8x to the 1, and that still has to be equal to 0. Solving for 8x, we get 8x is equal to 12. Divide both sides by 8. And we get x is equal to 12 on 8 is 6 on 4, which is 3 halves. Perfect. There's one more critical number. This is where our derivative equals 0. But what about when f prime of x does not exist? Well, if you look right here, f prime of x actually has an x in the denominator. So we know x also cannot be equal to 0. So this problem has two critical numbers. Our critical numbers are x is equal to 0, or x is equal to 3 halves. One of these are our two critical numbers. Found our function, took its derivative, set it equal to 0. Once you set it equal to 0, this is no longer a calculus problem. The algebra might be tricky, but you are just solving for the values of x that make this thing equal to 0. The other thing you have to ask yourself is, where does this derivative exist? Are there any rules of math I'm breaking? And we go, the only rule of math we can break right here is dividing by 0. So we have to include that point too. So, in terms of critical numbers, Fermat's theorem can be rephrased as so. In terms of critical numbers, Fermat's theorem can be rewritten as if f has a local max or local min at C, then C is a critical number of f. Then C is a critical number of f. So if we have this local maximum or if we have this local minimum, then we know we're going to have a critical number. This in the contrapositive says that if C is not a critical number, then you know there is no local max or local min. So we'll write that down again. So Fermat's theorem, or at least the contrapositive of Fermat's theorem, says that if the contrapositive to Fermat's theorem says that if C is not a critical number of f, then f does not have a local min / max at C. And at least now we're given something that we can really work with. If C is not a critical number, then we know it's not a local max or local min. Perfect. So what the contrapositive to Fermat's theorem says in terms of critical numbers is that if we're trying to find our local maximum and local minimums, we know that has to happen at this critical number. That's where the derivative is equal to 0, or when the derivative does not exist. So this is really the final form of our theorem. This is the form that we're going to use the most, and we're going to use it in some three-step process. I think we would hyphen that, a three-step process for finding absolute max and mins. So what we want to do now is we want to find the largest possible value for a function and the and the smallest possible value for a function. By smallest, I mean most negative, not closest to 0. So the first thing we're going to do is we need to find critical values for f. Find crit vals. Oh, then 2, we want to find vals of endpoints if they exist. And the third thing is just compare the largest value is absolute max, the smallest value is absolute minimum. So let's do some examples. Let's say we have the function f of x is equal to x cubed minus 3x squared plus 1 over negative 1/2 to 4. And what we want to do is we want to find the absolute maximum and find the absolute minimum of this function over this interval. So our 3-step process says the first thing we do is we find all of our critical numbers. Our critical numbers are where the derivative f prime of x, which is 3x squared minus 6x, is equal to 0. Well, we can divide both sides by 3 to get x squared minus 2x is equal to 0. Factor out an x, and that's when x is equal to 0 or x is equal to 2. So we have our 2 critical numbers. The other spot, this is where our derivative equals to 0. The other option is where our derivative doesn't exist. Well, our derivative is just a polynomial, and polynomials are continuous for every real number, so we know that this derivative exists for every real number. So our only 2 critical values, or our only 2 critical numbers, are x is equal to 0 and x is equal to 2. We will need their y values. So we need a f of 0, which would be just f, going back to the original. Now we're looking for the y value on this function that goes with this number. That's going to be 0 cubed minus 3 times 0 squared plus 1, where we get f of 0 is equal to 1. F of 2, because once again we're trying to find the y value on this function that goes with this x value. We get our x values from the derivative, but we get our y values from the original function. F of 2 is equal to 2 cubed minus 3 times 2 squared plus 1, which is 8, minus your 4, 3 times 4 is 12, plus 1, negative 4 plus 1 is negative 3. F of 2 is equal to negative 3. So we have this value we want to consider, and that value we want to consider. The second part of our process is that we want to consider the endpoints. So our second step is we want to figure out the y value that is associated with negative 1/2. That's going to be negative 1/2 cubed minus 3 times negative 1/2 squared plus 1, which is going to be a negative 1/8 minus, negative 1/2 squared is negative 1/4 times 3 is negative 3/4 plus, I'm gonna jump ship and write 1 as 8/8. Just kind of getting at what we're gonna have to. Negative 1/8 minus same denominator, that would make that a 6/8 plus 8/8 says that f of negative 1/2 is equal to a positive 1/8. And the final thing we want to do is consider the other endpoint, f of 4. Oh, and that would give us 4 times 4 is 16, times 4 is 24, or 64, minus 16 times 3, 48, plus 1. Well, if we got 64 and we take 48 from it, that's going to be 16 equals 17. Equals 17. Nice. F of 4 is equal to 17. So the final step, we're trying to find our absolute maximum and our absolute minimum. We have 4 things to consider. Our absolute maximum is going to occur at the largest value of y. Well, 17 is the largest value, so we know we have an absolute max, ABSO, absolute max at 417. Our absolute minimum, absolute, there's a B in that word somewhere. We want the smallest or the biggest in the negative direction value. So that's going to be -3. So our absolute minimum occurs at the point 2, -3. So this is what we do. We know that this function is horizontal here and here. We also need to check the values of the endpoints. Turns out this endpoint gives us the largest value from the function, but the minimum occurs somewhere in the middle of that function. So you find all the spots where your derivative is equal to 0, and you plug those values of x back into the original equation. Like I said, we use the derivative to find x values, we use the original to find y values. The derivative to find x values, and the original to find y values. We also have to find the y values of the endpoints. Step 3 is just picking and choosing. Pick the biggest one, pick the smallest one. Perfect. So for our final example, we have a story problem. The Hubble Space Telescope was deployed on April 24th, 1990 by the Space Shuttle Discovery. A model for the velocity of the shuttle during this mission from liftoff at t is equal to 0 out to t is equal to 126 is given by the following equation. V of t is equal to, and let me see, we've got 0.00130 t cubed minus 0.9029 t squared plus 23.61 t minus 3.083. So is given by, the velocity is given by this equation. And what we want to do is we want to estimate the maximum and minimum values of the acceleration over the interval 0 to 126. Perfect. So we're trying to find these maximum and minimum values of the acceleration. Acceleration, as a function of time, is equal to the derivative of velocity. And if we want the maximum and minimum values of acceleration, that means we're going to do most of our work with the derivative of a. Perfect. So our first step is going to be actually finding the equation that models acceleration. So a of t is going to be equal to, this multiplied by 3 is going to be 609300.0 t squared minus That's going to be 8508.1 t plus 23.61. And since we want to find the maximum and minimum values of acceleration, we need the derivative of acceleration. A of t is going to be equal to this number times 2 is going to be 218700.0 minus 1.8058. Perfect. And so our maximum and minimum values are going to occur at any critical point or at the endpoints. So we want to find our critical points or our critical values. We want to know where the derivative is equal to 0. And I forgot to write my t from this line going down. If that equals 0, that means we want to know where 0.07812t is equal to 1.8058. That's when t is equal to 1.8058 divided by 0.07812, which is about 23.12. So we know that we have this critical point in acceleration when t is equal to 23.12. The derivative of acceleration is also a polynomial, so it's continuous everywhere. That means we know that everywhere, for any value of t, this derivative exists. So we're okay there. There's no other critical values to worry about. So, if we want to find the maximum and minimum values of acceleration over this interval, now we test, in this problem, 3 points. We need to figure out what the acceleration was when t is equal to 0. Well, a of t is just going to be 23.61. We need to figure out the acceleration at the other endpoint. A of 126 is about equal to 62.87. And now we need to figure out the acceleration at this time, 23.12. And that's equal to 21.52. Perfect. So now we want to pick the largest and smallest values. Our maximum is going to occur here. This is our absolute max. Or the absolute maximum acceleration of this shuttle occurs when t is equal to 126. And the absolute minimum happens right here. Or the absolute minimum acceleration of this Hubble Space Telescope occurred 23.12 seconds into its takeoff. So this one was kind of tricky because they were asking about information about the acceleration and they gave us velocity, so we wound up having to take 2 derivatives. Remember to answer your question. Remember to answer what's being asked. They're asking about acceleration, so we had to plug everything back into acceleration. We weren't given acceleration, but we were given velocity, and we know how to work between the two. So, in large, this section is... So, in large, what we're doing in this section is we're taking a function. We're taking some function over a closed interval, a to b. We take the derivative of that function, and we set it equal to 0, and we solve for x. Something, something, something. We also care where in this interval f prime of x does not exist. However many points there are that satisfy all of these. Then what we're doing is we're taking this point, we're taking all of these points, and any of these points, in both the endpoints, and we're plugging them into whatever equation we're trying to maximize or minimize. Typically, we're going to plug it into the one that was given because we're trying to find the maximum and minimum values of a specific function. In this previous example, we plugged it into a different function, but that's because they were asking for something specific in that problem. You test your critical points, including the x values where this doesn't exist, and the endpoints in the original. Your maximum is just the most positive, the largest number you get. Your absolute minimum is the smallest, is the most negativist, the greatest in magnitude in the negative direction, if you will. Smallest is kind of ambiguous because 1/2 is smaller than -7,000. It's -7,000 is more negative, but 1/2 is smaller, so you want the most negative number for your absolute min. Hey, we got a back half. So for your homework, go off and do 3, 5, 20, 9 through 41, 47 through 59, and both of these are EOOs. Go and do every other odd for both of those. This is gonna give rise to curve sketching. We're gonna give some function of x, and based off of f of x, the derivative of f of x, and the second derivative of f of x, we're going to be able to sketch a curve. So pay careful attention to what we're doing and setting derivatives equal to 0. This idea kind of sets the stage for the entire rest of chapter 4. Taking derivatives, setting them equal to 0. So, like I said, this is the big takeaway. This is your guys' homework, and go ahead and send me an email if you guys have any question. Take it easy. Bye-bye.